Benford's law in everything. In 1938, physicist Frank Benford noticed something strange about the first digits of numbers in real-world datasets. Whether examining river lengths, stock prices, population figures, or physical constants, the number 1 appeared as the first digit about 30% of the time, while 9 appeared less than 5% of the time. This wasn't random chance. It was a precise mathematical pattern now called Benford's law. The law states that in many naturally occurring datasets, the first digit follows a specific logarithmic distribution. 1 appears 30.1% of the time, 2 appears 17.6%, 3 appears 12.5%, and so on, decreasing to 9 at only 4.6%. This distribution has been verified across thousands of different datasets from completely unrelated domains. Financial data follows Benford's law. Stock prices, tax returns, accounting records, and economic statistics all show this first-digit pattern. In fact, forensic accountants use Benford's law to detect fraud. Fabricated financial data almost never follows the pattern, because humans inventing numbers tend to distribute first digits more evenly. The IRS uses it to flag suspicious tax returns. But here's what's strange. The pattern appears everywhere. River lengths follow Benford's law. So do earthquake magnitudes, molecular weights of chemicals, numbers in scientific papers, baseball statistics, death rates, file sizes on computers, and the half-lives of radioactive isotopes. Why would the first digits of river lengths follow the same pattern as stock prices? What connects earthquake magnitudes to accounting fraud detection? These systems have nothing in common. Geology, finance, sports, chemistry, and computing are completely different domains governed by different physical laws. The mathematical explanation involves logarithmic scales and multiplicative processes, but this doesn't explain why so many natural phenomena happen to be logarithmic. It's as if reality has a built-in preference for certain numerical patterns, regardless of what's being measured. Researchers have tested Benford's law on increasingly obscure datasets. They found it in the Fibonacci sequence, in powers of 2, in physical constants from physics, in addresses on streets, in numbers mentioned in newspapers, and even in the sequence of prime numbers when expressed in certain ways. The pattern even appears in data that should be completely random. When you compile random numbers from different sources and perform certain mathematical operations on them, Benford's law emerges. Chaos produces order according to precise mathematical rules. What's most unsettling is that Benford's law suggests a deep connection between completely unrelated systems. The fact that one specific numerical pattern appears consistently across finance, geology, biology, physics, and human behavior implies some fundamental mathematical structure underlying all of reality. Some researchers have proposed that Benford's law emerges because reality operates on scale-invariant principles. The same patterns repeat at different magnitudes. But why should reality be scale-invariant? In a truly random universe, there's no reason for patterns to repeat consistently across different scales and domains. The existence of Benford's law suggests that even in apparently chaotic, unrelated systems, reality follows programming rules. The distribution of first digits isn't random. It's governed by mathematical laws so fundamental that they appear everywhere, as if reality is calculating these patterns rather than them emerging from physical processes. If you were programming a simulation and wanted to save computational resources, you might use logarithmic scaling and recursive patterns that apply across multiple systems. Benford's law looks exactly like what you'd expect from an efficiently coded universe where the same mathematical subroutines handle everything from river formation to stock trading to radioactive decay. The three-body problem's strange attractor. The three-body problem is a famous unsolved question in physics. Given 3 objects with mass attracting each other through gravity, predict their future positions. You'd think this would be solvable. We can predict 2-body systems perfectly. So adding one more object should just make the math more complex. But the 3-body problem is chaotic. Tiny changes in initial conditions lead to completely different outcomes. The trajectories are so sensitive to initial positions and velocities that long-term prediction is impossible. This is chaos in its purest form. deterministic equations producing unpredictable results. Yet within this chaos, patterns emerge. When mathematicians plot the possible trajectories of three-body systems in phase space, a multidimensional graph showing all possible states, they find strange attractors. These are complex geometric shapes that the system's trajectory tends to follow, despite starting from wildly different initial conditions. A strange attractor is a set of paths that chaotic systems gravitate toward. No matter where the three bodies start, their trajectory through phase space tends to trace out the same intricate, fractal-like structure. The system never exactly repeats, but stays within the bounds of this strange geometric form. This shouldn't happen in pure chaos. If the system were truly random and unpredictable, trajectories should spread out uniformly through all possible states. Instead, they cluster around specific geometric structures, mathematical forms that emerge from equations without being explicitly programmed into them. The Lorentz attractor is the most famous example, though it comes from weather modeling rather than gravity. It looks like a butterfly or figure-8 shape in three-dimensional space. Chaotic weather systems trace paths around this shape endlessly, never repeating exactly, but always following the attractor's structure. What's remarkable is that different chaotic systems produce similar types of attractors, despite having completely different underlying physics. Weather patterns, planetary orbits, chemical reactions, heart rhythms, and electrical circuits all exhibit strange attractors when analyzed mathematically. The geometric shapes differ in details, but share common mathematical properties. This suggests something profound. Chaos isn't actually chaotic. It's constrained by geometric structures that exist in abstract mathematical space. These structures aren't physical. They're purely mathematical objects that chaotic systems follow, as if they're rails guiding apparent randomness. Some physicists have noted that strange attractors look like compression algorithms. If you wanted to store the infinite complexity of a chaotic system using finite information, you'd use an attractor, a simple mathematical rule that generates complex behavior. The system never repeats, so it looks chaotic, but it's actually following a compressed instruction set. This is exactly how computer simulations of chaos work. Instead of calculating every possible trajectory, programmers define an attractor, a mathematical structure that constrains random behavior. The simulation produces chaotic motion that looks unpredictable but is generated from simple rules. The fact that real physical chaos follows strange attractors suggests reality might work the same way. Instead of infinite complexity, nature might be running compression algorithms, mathematical structures that generate apparently chaotic behavior from simple underlying code. If reality is programmed, strange attractors are what you'd expect to find. They're the fingerprints of computational efficiency in what appears to be pure chaos. Evidence that randomness itself follows rules, suggesting those rules were written by something. Quantum superposition collapse patterns. Quantum mechanics describes particles as existing in superposition, occupying all possible states simultaneously until measured. When you measure a quantum particle, the superposition collapses to a single definite state. Which state you get appears random, determined only by probabilities calculated from the wave function. This seems like fundamental randomness. No hidden variables, no predetermined outcome, just pure quantum probability. But the pattern of how superpositions collapse across many measurements reveals something strange. When you measure many identical quantum systems, the distribution of results follows precise mathematical patterns. These patterns match probability distributions calculated from quantum equations exactly, not approximately, but perfectly to many decimal places. Every prediction quantum mechanics makes about measurement statistics comes true with extraordinary precision. This is unusual for true randomness. If quantum collapse was genuinely random, truly uncaused and without underlying determinism, there'd be no reason for the statistical patterns to match mathematical predictions so precisely. Random should sometimes deviate from predictions just by chance. But quantum measurements never deviate from predicted statistics. Run 1,000,000 identical experiments measuring electron spin, and the ratio of up to down results will match the calculated probability to absurd precision. The randomness is perfectly controlled randomness. It follows rules exactly. Some quantum systems exhibit even stranger patterns. Quantum tunneling, particles passing through energy barriers they shouldn't be able to cross, happens at rates calculated precisely from wave functions. The phenomenon appears random for individual particles, but the statistical pattern across many particles is perfectly predictable. Quantum entanglement shows correlated randomness that's even more peculiar. When two particles are entangled and you measure one, the other instantly shows a correlated result regardless of distance. Each individual measurement seems random, but the correlation between measurements is perfect, exactly matching quantum mechanical predictions. This suggests quantum randomness isn't random at all. It's pseudo-random, generated by deterministic rules that produce results that look random but follow precise statistical patterns. This is exactly how random number generators work in computers. They use deterministic algorithms that produce sequences appearing random but actually generated from seed values and computational rules. The delayed choice quantum eraser experiment reveals something even more bizarre. The experiment shows that measurements made after a photon is detected can retroactively determine what path the photon took earlier. Cause appears to follow effect, as if reality is being calculated backwards to maintain consistency. This makes no sense if quantum events are physical processes unfolding in time, but it makes perfect sense if reality is computational, if the universe is rendering outcomes based on all boundary conditions, calculating backwards and forwards simultaneously to maintain mathematical consistency, like a computer solving a puzzle by considering all constraints at once. Some physicists have proposed that quantum mechanics is essentially information theory. Particles aren't physical objects, but information states, and measurements are information extraction processes. The wave function isn't a physical wave, but a probability distribution representing information about possible states. If this interpretation is correct, quantum randomness is generated by information theoretic rules, exactly what you'd expect if reality is a simulation running quantum algorithms. The patterns in quantum collapse aren't emerging from physical randomness, but from computational processes generating pseudo-random outputs. The perfection of quantum statistics, the fact that measurement patterns never deviate from calculated probabilities, suggests we're seeing computer-generated randomness rather than true physical randomness. Reality appears to be executing a quantum program, and the patterns we observe are artifacts of that program's operation. Cellular automata producing complexity. In 1970, mathematician John Conway created the game of life, a cellular automaton consisting of a grid of cells that follow three simple rules. A living cell with 2 to 3 neighbors survives, a dead cell with exactly 3 neighbors becomes alive, and all other cells die or stay dead. These rules are applied simultaneously to every cell, generation after generation. From these trivial rules, extraordinary complexity emerges. Patterns called gliders move across the grid. Glider guns shoot out streams of gliders. Structures can compute, store information, and even replicate themselves. The system is Turing complete, meaning it can perform any computation a computer can. What's remarkable is that this complexity isn't programmed in. Conway didn't design gliders or guns. They emerge spontaneously from the 3 simple rules applied to random initial conditions. Complex behavior arises from simplicity through iteration. Cellular automata reveal something profound. Reality might be computed from simple rules that generate complex patterns. Our universe's apparent complexity, galaxies, life, consciousness, might emerge from simple underlying rules iterated across space and time, just like the game of life. Stephen Wolfram explored this idea extensively in his work on computational theory. He studied cellular automata systematically, cataloging different rule sets and their behaviors. He found that many simple rules produce complex, apparently random patterns, what he called computational irreducibility. Computational irreducibility means the only way to know what a system will do is to run it. You can't predict the outcome faster than the system computes it naturally. The pattern can't be compressed into a simpler description. The system itself is the simplest description of its behavior. Wolfram found that Rule 110, one of the simplest cellular automata, is Turing complete despite having just 2 states and a 3-cell neighborhood. This incredibly simple rule can perform universal computation. Complex behavior emerges not because the rules are complex, but because iteration reveals computational depth. This suggests reality might work similarly. The laws of physics might be simple rules, perhaps as simple as cellular automaton rules, that generate all observed complexity through iteration. Particles, forces, and space-time might be emergent phenomena from underlying computational substrates. What's most intriguing is that cellular automata exhibit phase transitions. At certain parameter values, the system shifts from ordered behavior to chaotic behavior, with a narrow boundary where complexity is maximized. This edge of chaos is where interesting computation happens, where order and randomness balance to create rich patterns. Physical reality appears to exist at a similar edge of chaos. The universe's constants and parameters sit in a narrow range where complexity is possible. Slightly different values would produce either boring order or useless chaos. Reality appears fine-tuned to sit at the computational sweet spot. If you were programming a simulation, you'd want to use simple rules that generate complex behavior through iteration. Exactly what cellular automata do. You'd tune the parameters to sit at the edge of chaos where interesting phenomena emerge. You'd design a system that's computationally irreducible so inhabitants can't predict everything and discover they're simulated. The patterns in cellular automata look eerily similar to patterns in nature. Gliders resemble particles. Self-replicating structures resemble life. Computational depth resembles physical laws. The parallels suggest our universe might be a cellular automaton, running on an unimaginably large grid with rules we perceive as physics. The fact that simple rules can generate all this complexity without being explicitly programmed suggests that reality's complexity might also be emergent rather than fundamental, calculated rather than existing intrinsically, programmed from simple axioms rather than infinitely detailed from the beginning. The fine structure. Constant's precision. The fine structure constant, denoted A, alpha, is a dimensionless number approximately equal to 1/137. It characterizes the strength of electromagnetic interaction between charged particles. This number appears throughout physics, in atomic spectra, quantum electrodynamics, and the energy levels of atoms. What makes this constant remarkable is its precision and its arbitrary value. It has no units. It's a pure number. It doesn't depend on human choices of measurement systems. It's the same in any units, representing a fundamental ratio in nature. The value is 0.072973525693, approximately 1/137.03599084. This number has been measured to extraordinary precision, and theoretical calculations match measurements to 10 decimal places. The electron's magnetic moment, calculated using the fine structure constant, agrees with experiment to 12 significant figures, one of the most precise confirmations in all science. But why this number? Why not 1/100 or 1/200? The fine structure constant has no known mathematical origin. It's not P or E or any combination of mathematical constants. It appears to be arbitrary, set by no underlying principle we can identify. Yet this arbitrary number is fundamental to reality. If SA were different by more than a few percent, chemistry would be impossible. Atoms wouldn't form stable structures. Stars couldn't produce heavy elements. Life couldn't exist. The value sits in a narrow range permitting complexity. Physicist Richard Feynman called the fine structure constant one of the greatest damn mysteries of physics, and said all good theoretical physicists worry about it. He noted that the number should somehow emerge from deeper theory, but doesn't. It's just there, unexplained, yet essential for everything. Some researchers have looked for patterns in the digits, wondering if the number encodes information. The approximation 1/137 has led to numerological speculation, though most physicists dismiss this. But the question remains, why this specific value and not another? The fine structure constant also appears stable across cosmic time and space. Measurements of light from distant galaxies suggest A has remained constant for billions of years and across billions of light years. Whatever determines this value set it at the universe's beginning and maintains it everywhere consistently, This looks like a parameter in a simulation, a number set at initialization that determines how the program runs. If you were coding a universe, you'd have constants like A as inputs that define how forces behave. The fact that reality has unexplained dimensionless constants that are precisely fine-tuned suggests someone set them. More mysteriously, the fine structure constant connects to other fundamental constants through relationships that seem too elegant to be accidental. Some formulas relating A to other constants have been proposed, though none are universally accepted. The connections hint at deeper mathematical structures we don't yet understand. The number's precision is also notable. Nature doesn't usually produce irrational numbers to arbitrary precision. Physical measurements have limits, yet AA can be calculated and measured to many decimal places, all agreeing perfectly. This precision suggests it's derived from mathematical rules rather than physical processes. If reality is programmed, fundamental constants like A are what you'd expect. Arbitrary input parameters set to specific values that make the program run correctly. The fine-tuning, the precision, the arbitrary value, and the universal constancy all point toward a designed input rather than a randomly emergent property. The fine structure constant's existence and properties suggest reality runs on a program with parameters, and someone or something chose those parameters very carefully. Fractal dimension. In natural chaos. Fractals are geometric shapes that show self-similarity at different scales. The same pattern repeats whether you zoom in or out. They are described by fractal dimension, a number that doesn't have to be an integer and measures how completely a fractal fills space. What's remarkable is that chaotic natural phenomena consistently produce specific fractal dimensions. Coastlines measure around 1.25. Mountains and terrain typically measure around 2.2. Clouds measure around 2.3, 2.4. These aren't random values. They're consistent across different examples of the same type of phenomenon. The fractal dimension quantifies complexity in a precise mathematical way. A perfectly smooth line has dimension 1. A completely filled plane has dimension 2. Fractals fall in between. A coastline is more complex than a straight line, but doesn't fill an entire plane, so its dimension is between 1 and 2. Why do different coastlines worldwide, formed by different geology, erosion, and processes, converge on the same fractal dimension around 1.25? Why do clouds from different weather systems consistently measure 2.3, 2.4? These phenomena should be chaotic and variable, yet they produce mathematically consistent results. The explanation is that fractal dimension reflects the underlying processes generating the patterns. Coastline erosion follows certain physical principles that consistently produce a specific type of complexity. Cloud formation follows fluid dynamics that generate characteristic fractal structures. But this just pushes the question back. Why do diverse physical processes converge on producing fractals with consistent dimensions? It's as if nature has a limited toolkit of fractal generators and applies them everywhere appropriate. Some researchers have discovered that optimal solutions to certain problems naturally produce specific fractal dimensions. Trees branch fractally to maximize surface area for nutrient transport. Blood vessels branch fractally to efficiently distribute blood. Lungs branch fractally to maximize gas exchange surface within limited volume. These biological fractals have dimensions around 2.0, 3.0, and remarkably, different organisms converge on similar values. Human lungs, tree roots, fungal networks, and river drainage systems all show similar fractal branching, despite being completely different biological or geological systems. The convergence suggests fractal patterns aren't random outcomes of chaotic growth, but solutions to optimization problems. Nature is solving equations, finding geometries that maximize efficiency, and these optimal solutions are fractal with specific dimensions. This is computational thinking. If you were programming efficient systems, you'd use fractal algorithms because they're mathematically optimal for distribution and surface area problems. The fact that nature consistently produces the same fractal dimensions suggests it's running optimization algorithms. Mandelbrot, who pioneered fractal geometry, noted that fractal dimension could be measured and predicted mathematically even for chaotic systems. You can calculate the fractal dimension a system should produce based on its rules, then measure actual examples and find they match predictions. This predictability within chaos suggests underlying order. Chaotic processes aren't actually random. They're following mathematical rules that guarantee specific fractal dimensions. The patterns are programmed into the physics. Computer-generated fractals and natural fractals are mathematically identical. You can't tell them apart by measuring fractal dimension. This equivalence suggests natural chaos might be computationally generated, calculated according to the same algorithms we use to create artificial fractals. If reality is a simulation, fractal dimension is a signature of efficient coding. Instead of storing infinite detail, you use recursive algorithms that generate detail at all scales. The consistent fractal dimensions appearing in natural chaos suggest we're seeing the output of such algorithms, reality rendering complexity through mathematical rules rather than containing actual infinite detail. Turbulence following universal patterns. Turbulence is the paradigm of chaos, swirling, unpredictable fluid motion that's notoriously difficult to calculate. Yet turbulent flows follow surprisingly universal patterns described by precise mathematical laws. The Kolmogorov power spectrum describes how energy distributes across different scales in turbulent flow. Despite turbulence being chaotic, energy distribution follows a specific mathematical relationship. The energy at scale L is proportional to L to the power of 5(3). This relationship holds for turbulence in water, air, plasma, and even galactic gas clouds. Why would chaotic flows in such different materials and conditions all follow the same mathematical power law? Water turbulence, air turbulence, and interstellar turbulence have vastly different physical properties, yet they obey identical statistical rules. The explanation involves energy cascade, large eddies breaking into smaller eddies, transferring energy from large scales to small scales, where it dissipates as heat. But this just describes the process, not why it produces such precise mathematical patterns. Richardson's law describes how neighboring particles in turbulent flow separate from each other over time. The separation distance grows proportionally to time to the power of 3(2). This relationship holds across different fluids and flow conditions. Another universal pattern in chaos. Turbulence also exhibits intermittency, brief bursts of intense activity separated by calmer periods. The statistics of intermittency follow multifractal distributions with specific scaling properties. Different turbulent systems show similar intermittency patterns, despite having nothing in common physically. Most remarkably, turbulence shows predictable patterns in what should be purely chaotic conditions. Researchers have found that coherent structures, organized patterns like vortices, spontaneously emerge from turbulent chaos. These structures form, persist, and interact in ways that can be partially predicted despite the overall chaos. Some turbulent flows exhibit strange attractors. The system's state traces paths through a specific geometric structure in phase space despite apparent chaos. The attractor's geometry reveals hidden order within turbulence. Scientists studying turbulence have noticed that different systems show similar statistical properties when analyzed using information theory. The entropy, information flow, and complexity measures are consistent across different types of turbulence, suggesting underlying computational similarities. The universal patterns in turbulence suggest that chaos follows rules, not just the deterministic equations that generate it, but statistical and structural rules that emerge consistently regardless of specific conditions. It's as if turbulence is a standard subroutine that reality runs whenever certain conditions are met. If you were programming fluid dynamics in a simulation, you'd use universal turbulence algorithms that work across different fluid types and scales. You wouldn't code each instance of turbulence separately. You'd use general mathematical rules that generate chaotic-looking behavior efficiently. The fact that real turbulence shows these universal patterns suggests nature might be doing the same, running standard algorithms that generate controlled chaos according to precise mathematical rules, producing the illusion of randomness while actually following programming constraints. Self-organized criticality in avalanches. In 1987, physicist Per Bach discovered a phenomenon called self-organized criticality, while studying sand pile models. He found that if you gradually add sand grains to a pile, the pile naturally evolves toward a critical state, where avalanches of all sizes occur according to a precise mathematical pattern called a power law. In self-organized criticality, the system automatically tunes itself to a critical point without external control. Small avalanches happen frequently, medium avalanches less often, and large avalanches rarely, following a specific mathematical distribution that can be predicted even though individual avalanche timing and size are unpredictable. The remarkable discovery was that this pattern appears throughout nature. Earthquakes follow power law distributions. Small earthquakes are common, large ones rare, with a precise mathematical relationship called the Gutenberg-Richter law. Forest fires follow similar power laws. So, do solar flares, mass extinctions, stock market crashes, and neural avalanches in brains. These systems have nothing in common physically. Earthquakes involve tectonic stress. Forest fires involve combustion. Solar flares involve plasma. Stock crashes involve human behavior. And neural avalanches involve neurotransmitters. Yet all exhibit the same statistical pattern. Why would geological, biological, astrophysical, economic, and neurological systems all converge on identical mathematical distributions? There's no physical reason for sand avalanches and stock market crashes to follow the same power law. They're completely different phenomena. The answer appears to be that self-organized criticality is a universal behavior of complex systems with many interacting components. When such systems accumulate stress or energy gradually and release it suddenly, they naturally evolve toward a critical state exhibiting power law behavior. But this universality is itself remarkable. It means that regardless of specific physical details, systems with certain abstract properties will behave identically. The mathematics transcends the physics, as if reality is implementing general algorithms that apply across different physical substrates. Researchers studying self-organized criticality have found it arises naturally in cellular automata and network models with simple rules. Computer simulations reproduce the power law patterns observed in nature, suggesting these patterns emerge from computational rather than physical principles. The power law exponents, the specific numbers characterizing the distributions, are often similar across different systems. Earthquake magnitude distributions and neural avalanche distributions show similar exponents despite having nothing physically in common. This suggests shared underlying mathematics. Some physicists have proposed that reality operates near criticality across multiple scales and domains. The universe might be tuned to a critical state where complex behavior emerges, sitting at the edge between order and chaos, where interesting patterns and structures can form. This criticality might not be coincidental. If reality is programmed, you design it to operate near criticality, because that's where complexity and computation are maximized. Self-organized criticality provides a mechanism for generating interesting behavior without constant fine-tuning. The system tunes itself. The fact that such diverse phenomena exhibit identical statistical patterns suggests they're produced by similar algorithms. Whether it's sand grains, tectonic plates, neurons, or stock traders, the underlying process might be computational rather than physical. Reality executing general-purpose programs that generate power law distributions, regardless of physical details. Self-organized criticality reveals that chaos has structure. Avalanches are unpredictable individually, but perfectly predictable statistically. This structured randomness looks like programmed pseudo-randomness rather than true physical chaos. Information conservation in black holes. Black holes are among the most extreme objects in the universe, regions where gravity is so strong that nothing, not even light, can escape. According to classical physics, anything falling into a black hole is gone forever, and all information about it is lost. But quantum mechanics demands information conservation. Physical information can't be destroyed, only transformed. This creates the black hole information paradox. Classical relativity says information is lost. Quantum mechanics says it can't be. And both theories are well tested and accurate in their domains. Recent theoretical work suggests information isn't actually lost, but is somehow preserved in subtle ways. Stephen Hawking ultimately conceded that information must be conserved, though the mechanism remains unclear. The resolution likely involves understanding how quantum mechanics and gravity combine. Quantum gravity theory that we don't fully have yet. What's remarkable is that the universe appears to treat information as fundamental. The information content of any region of space seems to be finite and calculable, using formulas involving surface area rather than volume. This holographic principle suggests reality is fundamentally informational. The Bekenstein bound quantifies the maximum information that can be contained in a region of space. It depends on the region's surface area and energy content, giving a finite number of bits that could theoretically be stored. The universe has limits on information density. These limits look exactly like limits on computational storage and processing. If reality is a simulation, you'd expect finite information capacity because you have finite computational resources. The universe behaving as if it has information limits suggests it's running on something with actual computational constraints. Black hole entropy. The information content of a black hole is proportional to its surface area, not volume. This is bizarre for physical objects, but natural for information storage. A 2D surface encoding 3D volume is exactly what holograms do, and it's an efficient way to compress information. The fact that physical entropy follows informational rules rather than spatial rules suggests reality is informational at its foundation. Space might be emergent from information, not the other way around. Reality might be rendering 3D space from 2D informational substrates. Quantum entanglement shows information correlation that seems to ignore space. Entangled particles are informationally connected regardless of distance. This non-local correlation looks like particles sharing computational states rather than being physically connected. Information links transcend spatial separation. Some physicists have proposed that space-time itself emerges from entanglement patterns. Quantum information relationships generate the geometry of space. If true, this makes space a calculated property rather than a fundamental container. Reality would be computing space from information rather than having information exist in pre-existing space. The black hole information paradox resolution suggests the universe operates according to information theoretic principles more fundamental than physical laws. This is what you'd expect if reality is computational. Information conservation isn't a physical property, but a programming constraint. Even the speed of light might be an information limit, the maximum rate at which information can propagate through the simulation. Quantum field theory describes particles as information excitations. The standard model could be interpreted as information processing rules. The patterns in how physical systems handle information, the conservation laws, the entropy relationships, the holographic principle, the computational limits, all suggest reality treats information as primary and matter energy as derivative. This is the signature of a programmed universe where information is the actual substrate and physics is the rendering engine. Delayed choice, quantum eraser. The delayed choice quantum eraser experiment reveals something deeply strange about causality. In this experiment, a photon's behavior is determined by a measurement made after the photon has already been detected, suggesting future events influence past outcomes, or that reality is computing backwards to maintain consistency. The experiment involves sending photons through a double-slit apparatus. Normally, photons create an interference pattern, indicating they behave as waves traveling through both slits simultaneously. If you measure which slit a photon goes through, the interference pattern disappears. The photon behaves as a particle going through one slit. In the delayed choice version, experimenters can choose whether to measure which path information after the photon has already passed through the slits, and even after it's been detected on a screen. Remarkably, whether interference appears depends on measurements made later in time. If which path information is measured, even after detection, no interference pattern appears in the data subset corresponding to that measurement. If which path information is erased, again after detection, interference pattern appears in that data subset. The photon's past behavior changes based on future measurements. This doesn't involve faster-than-light signaling. You can only see the pattern by correlating data from both detection points. But It does suggest reality isn't computing forward in time linearly. Instead, outcomes appear to be determined by considering all boundary conditions, past and future, simultaneously. From a computational perspective, this makes sense. If reality is solving constraint satisfaction problems, finding histories that satisfy all measurement constraints, it would calculate backwards and forwards simultaneously. The photon's behavior would be determined not by its past alone, but by all measurements made on it or its correlated partners. This is exactly how modern computational physics works. When simulating quantum systems, computers don't just calculate forward in time. They use algorithms that consider all boundary conditions and find solutions satisfying all constraints simultaneously. The universe appears to work the same way. The experiment shows that what happened isn't determined until all relevant information is available. Reality seems to retroactively compute history to maintain consistency with all measurements. The past isn't fixed until the future constrains it. This suggests time might not be fundamental. If reality is computational, time could be a dimension along which calculations are performed rather than something that flows. Past and future would be equally real in the computation, both just boundary conditions the solution must satisfy. Several quantum experiments show similar retrocausal patterns. Quantum teleportation requires measurement choices that can be made after the teleported state has been transmitted. Entanglement swapping can connect particles that never interacted by manipulating their entangled partners after they've separated. These phenomena suggest reality doesn't render detailed history as events occur. Instead, outcomes are computed as needed, based on what's measured. Unmeasured events remain unrendered, existing in superposition, until measurement forces reality to calculate a specific history, satisfying all constraints. This is computationally efficient. If you're running a simulation, you don't calculate every detail of every possible outcome. You calculate what's needed when it's observed, ensuring consistency with what's been computed previously. Reality appears to work this way, rendering details on demand rather than maintaining complete detailed history. The delayed choice quantum eraser suggests we're seeing artifacts of how reality computes, evidence that causality isn't fundamental, but emerges from computational processes that work across time, calculating solutions to constraint problems rather than simply evolving forward through time. 10 patterns in chaos, 10 mathematical structures emerging from randomness, Benford's law in everything, strange attractors constraining chaos geometrically, quantum statistics perfectly matching predictions, cellular automata generating complexity from simple rules, the fine structure constant precisely fine-tuned, fractals showing consistent dimensions, turbulence following universal power laws, self-organized criticality producing identical distributions, black holes treating information as fundamental, quantum experiments computing backwards through time. These aren't coincidences. They're precise mathematical patterns appearing consistently across unrelated domains: quantum mechanics, geology, economics, cosmology. If chaos was truly random, these patterns wouldn't exist. If they did emerge, they'd be approximate and variable, not exact and universal. The standard explanation says mathematical order emerges from physical laws naturally, but this misses the point. Why do physical laws produce such consistent patterns across unrelated systems? Why is chaos so precisely mathematical? A programmed universe would show exactly these patterns. Fractal recursion for efficient detail, cellular automata, rules generating complexity, power law distributions from self-organized criticality, fine-tuned constants enabling complexity, retroactive calculation maintaining consistency, information's conservation as a computational constraint. Reality doesn't just follow laws, it appears to execute programs. The mathematical precision, universal patterns, computational efficiency, and information theoretic limits suggest we're observing a computational system rather than a purely physical one. If you were building a simulated universe, you'd use efficient algorithms generating apparent complexity. You'd implement universal mathematical rules applying across different phenomena. You'd set computational limits determining what's possible. The patterns in chaos aren't emerging from randomness. They're evidence that chaos itself is programmed, designed to look random while following precise mathematical rules. We might be living inside a program so sophisticated that even its chaos follows code.